Thank you.
Yeah.
So thank you for the invitation. So I've been here once, a long time ago. And I remember there was a huge winter storm when I came, so I hope this time will be better. Hopefully. Okay, so this is the title of my talk. So I guess I don't have to insist very much on the fact that there is dark matter in the universe. And yet we don't know exactly what it is made of, although some people have an opinion about that. So the problem, of course, is that there is a whole zoo of possible dark matter candidates, and I guess you are familiar with this picture. In my talk, I'm going to focus on so-called WIMP, that is weakly interacting massive particles. Okay, so very briefly, the idea is that the dark matter particles is stable, but it may annihilate into standard model particles. And then the relic abundance is basically fixed by a so-called thermal freeze-out. When the dark matter becomes non-relativistic, its abundance gets frozen at a value which is basically fixed by the so-called annihilation cross-section, which is the cross-section times the relative velocity of the particle. And this is the benchmark value that you have all in mind when you think of WIMP particles. So WIMPs are nice. One reason being this so-called WIMP miracle, the fact that if you have a weak scale cross-section, then perhaps you have a natural explanation for the origin and the nature of dark matter. The other aspect, of course, is due to the fact that if you cross the diagram, the one that gives you the relic abundance, then you may have other probes of way of probing the nature of the dark matter particle. Here you have dark matter particles scattering on standard model particles, and this opens the possibility of having so-called direct detection of dark matter. And then, by the same token, dark matter may annihilate today, not in the universe, but today, say at the galactic center, into standard model particles, and that opens the possibility of seeing dark matter indirectly. And then, of course, the new big game in town is to try to produce dark matter at colliders, that is the LHC. Here, dark matter is supposed to be made of neutral particles, so to actually see something, you need some extra probe here, illustrated by the emission of, say, a gluon. Okay, so basically the signal is jet plus missing energy. Yes. Of course, problem, even if you focus on WIMPs, there are many possibilities. Okay, so this is supposed to be sort of illustrated by this picture. Actually, there are many candidates on this picture which are not WIMPs, okay, like axions, etc. But anyway, it's supposed to illustrate the fact that we have many possibilities, and we actually don't know. Well, actually, I don't know what's supposed to illustrate, but certainly there are many possibilities. Okay, and somehow the fact that you have so many possibilities, and also a related embarrassing issue, which is that we don't have indication of physics beyond the standard model at the LHC, okay, has motivated a sort of effective model-independent approach to dark matter, and more specifically to dark matter constraints. So here you have two illustrations of that. Okay, this is a dimension 6 operator. So here dark matter is supposed to be a decay particle, which for illustration is taken to be, say, a Dirac fermion. Okay, and then it may couple with the standard model quarks for some vector interaction. Okay, so that is in the UV, you may have some new vector particle. Okay, in the infrared, you get an effective operator like that, which dimension is 6. Okay, that is suppressed by some unknown scale to the power 2. And but that's one possibility. Another possibility is this kind of operator, different dimension, dimension 7. That means here that you have lambda to the 3 instead of lambda to the square. And here you have the possibility of having, say, annihilation into gluons. Okay, so in the UV they are quite different, but you have these two operators. Okay, they are just illustrations. Okay, and then what you can do with that. So this is an introduction. So I guess you are familiar with that. But one has to start somewhere. okay, is that you, for instance, using these effective operator, you may compare the constraints you have from direct detection, which are shown here for a few experiments. Okay, here is the latest one, Lux, okay, 2013. And you constrain the properties of the dark matter in the mass versus cross-section on nucleon plane. Okay. And in the same plane, you may report the limit that you get by looking for missing ET plus jets signals at DLHC. You don't see any excess on top of standard model physics, so that puts constraints on these operators, and these are these regions. Okay. And so here, again for illustration, you have the one for this vector black operator, and here for this dimension 7 operator. And something you may notice, okay, which is a bit surprising, is that there is this large difference between somehow the performance of the two operators. Okay, this is the constraint on this seems to be much stronger than the constraint on that. Okay, and that's sort of surprising, but it's very simple to understand. Okay, basically, at the LHC, you have a little difference between quarks and gluons. Okay, they're essentially partons. Okay, so when you look for jets plus missing ET, basically you probe some scale, so which is very much the same for quarks and gluons. Okay, but then when you report that in that plane, okay, the scaling that you get is very different, because here you have a dimension 7 operator, here you have a dimension 6 operator, and that is the reason why you get so much, so very, different things. So that seems to be very much constrained, and the constraint is much stronger than on this one, but this is all related to the spurious fact that you have operators with different dimensions. Okay, but the underlying physics is the same. Okay. And there are all sorts of issues related to the use of effective operator, which I'm not going to review, but basically which are related to the fact that it's not always self-consistent, because basically you are constraining, you get a constraint on some scale, but that scale may turn out to be, say, lower in energy than actually the scale that is probed at the collider. Okay, say, you may say that the effective scale is probed to be higher than 300 GeV, while the physics that you are probing is in 50 GeV scale. Okay, so effective approach is not always consistent. It may tell you that something is excluded and another thing is not yet excluded, etc. But that may be due to the scaling between infrared and UV, which is different for different operator. The wind miracle is not built in. Okay, you have no. It's not clear that it's the same operator which is relevant for the relic abundance that you're actually probing at the LHC. So this may not be an issue, but okay, certainly, I mean, whatever you do, you have some loss of somehow significant information. And that somehow has motivated people to look at sort of the next step, which is to look at so-called simplified models. Okay. So what are simplified models, where they sort of stand midway between this effective operator approach, okay, in which you have basically one scale, one particle, okay, and more fundamental theories like supersymmetry, extra dimension, whatever. Okay, so a simplified model is sort of sit in between, okay, and they are a bit more complicated than effective operators. But still, they contain few parameters, like typical masses, couplings, okay, you have few particles, okay. And if anything, they provide a consistent correspondence between different searches, okay. You don't have the issue raised by the operator. Or if you want, in some other language, you have a model which is normalizable, say, and then you can do calculations, they are reliable, and you may compare two experiments, okay. And they are perhaps narrow in scope, okay? I mean, usually they can't explain everything, okay? But they are nevertheless very instructive, okay? Because either confirmation or rejection tell you something, okay? First, if the prediction of the model is confirmed, it's obvious that you learn something. If it's rejected, it means that the things may be more complex, etc. So they point in a specific direction. Okay. So, of course, simplified model is a sort of a funky name for something that people have been doing forever, okay, which is sort of, models, okay, but it's sort of the fashionable name for something. So here I'm basically going to discuss two simplified models. One is a Z-prime model, and I'm going to discuss what you learn with this kind of model, or may learn from this kind of model, in particular when you look at the confrontation of LHC effects and direct detection searches. And then the other model, which I call vector-like model, will be discussed later on, and there we'll focus on gamma ray feature, that is indirect detection. Okay, so it's sort of a mixed presentation of different things that I've been working on. Okay, so on that part, this is quite easy, so I'll go fast on that, and here we'll spend a bit more time because I think it's sort of nice. Okay, but the big difference, if you want to say take something home, is that in that case, say dark matter annihilation is through a new particle in the S channel, or in that case, there is a new particle, but it's in the T channel. And that's sort of two generic categories of model. Okay, so it's illustrative of two big, trends. Okay, so first the Z-prime model and complementarity between LHC and direct detection searches. So the thing I want to illustrate is actually quite basic, but it's something which from scratch is lost when you use effective operator. Okay, and so you consider this diagram. In this diagram, you have coupling of this dark matter particle through the Z-prime particle to standard model fermions, and of course, by the same token, you have this kind of process. Okay, that means that at low energy, you have this effective operator, but it's related to that effective operator. And if here you have quarks and leptons, you also have this kind of operator. Besides, the Z-prime may be produced resonantly. Okay, so of course something impossible to get with an effective operator. So let's look at one specific resonant effect, and this is the projection of dileptons, at the LHC. Okay, so of course so this is the data and the standard model background as a function of the center of mass energy. Okay, actually this is invariant mass, sorry. And here of course you have the Z peak, okay, and then you may look for other resonances, okay, something like analogous to that but at higher mass, and basically you see nothing in the data, and so you put constraints on the existence of possible new resonances like this Z-prime particle. So this is another way of presenting the same thing. Here you have the mass of the Z-prime particle. Okay. Here you have the branching into dileptons. Okay. Well, actually the number of even is branching in dileptons. And here you have the constraint from the LHC. And this you may want to compare to a specific model. So just for the sake of illustration, I will focus on very naive model, which is called the sequential standard model. That is basically there is a Z prime, but it's a sort of a copy of the Z. Okay, same coupling, etc., but different mass. Okay, it's just a simple model. Okay, one unknown, which is the mass of.
How much this changes actually if you have like different couplings of the Z prime? Like if you have like not exactly a copy of Z prime, you start playing.
Actually, there are two models. I mean, like here you have an illustration of this. This is another model from E6. Okay, so this is the standard model sequential model, and here you have this E6 inspired model, different couplings, because different unification of couplings, etc. Okay, so there is a slight change, okay, but nothing really dramatic. Okay, but certainly what you see from this plot is that anything which is lighter than that, okay, is excluded by the LHC searches. Okay. Now, what I'm going to consider is the possibility that the Z prime, okay, is coupled to some hidden sector. Okay. there are different ways of doing that. One way being, for instance, kinetic mixing. Okay. Then in that case, it may be that on top of some visible branching, okay, there is some invisible contribution. Of course, here I'm assuming that the dark matter is lighter than half the mass of the Z prime. Okay, and so you have some invisible branching, and of course, so it's phenological what I'm doing. Okay, basically I'm going to play with the fact that you may increase the branching, the invisible branching of this particle. Okay, but of course if you do that, okay, you make the Z prime less visible at the LHC, but by the same token, it's coupled to, you introduce a coupling between dark matter and the visible matter. Okay, and in that case, you get constraint from a direct detection experiment. So this is sort of illustrated by this schematic plot. Okay, so here's the visible branching of the Z prime plus the invisible branching, and of course, the sum must be equal to 1. Okay. And here you have the same plot as before. So this is something which is the number of events you expect to have. Okay. And of course, the larger the visible branching, the larger the number of events. Okay. This is again the mass of the Z prime. Okay. So this is what you get from experiment. And one way of decreasing the constraint from LHC, okay, is by decreasing the visible branching. Okay, so this theoretical limit here of prediction, okay, goes down if you increase if you decrease the visible branching. Okay, but at the same time, you may look at the direct detection plane. So here you have the mass of the dark matter, and here you have what is effectively the coupling between the dark matter and visible matter, which is, proportional to this visible branching. Okay, here you have the explicit exclusion from direct detection experiments, and of course, if you start increasing the coupling between the dark matter and the visible matter, okay, then you have this region which goes up. Okay, so they go in opposite direction. Okay, so this is more, so that was a sketch of the situation. Okay, so let me try to explain. So again, this is the exclusion on from LHC. So anything which is above, okay, is excluded by LHC. Okay, and here I consider different candidates. Okay, so this is first a candidate which has mostly spin-independent interactions. Okay, for instance, if you have vector, if your coupling is essentially vector-like, okay, if the dark matter has a mass of 50 GeV, okay, you have a pretty strong constraint from direct detection. Okay, this is what the constraints from direct detection are the largest. Okay, and so basically whatever is below this line is excluded by direct detection searches. Okay, so this is excluded from above by LHC, and it's excluded from below by direct detection. Now, if you take a AGV dark matter candidate, okay, for light dark matter candidate, the constraints from direct detection are weaker. Okay, so you may have a stronger coupling to the Z prime. Okay, and the constraints are, and so you can make it more invisible, and so this exclusion limit drops. Okay, and you get to this point. Okay. Another way of weakening, if you want, the constraint from direct detection is to assume that instead of having a vector-like coupling to dark matter to quark, you have the axial vector, which is spin-dependent. Okay, spin-dependent direct detection searches are weaker than spin-dependent searches. Okay, and so you can make your Z prime even more invisible. Okay, and you get a limit like that, or something which is actually even weaker. Okay, so that's one way of seeing that. The other way is again to look at the direct detection plane. Okay, so the mass of the dark matter, the spin here. I'm showing a spin-dependent cross section. Okay, the exclusion from lux. Okay, and again in this plot, for a given fixed Z prime mass, whatever is below is excluded. Okay. So here, basically, what I'm illustrating is something which is usually not put forward. Okay, if you go back to the constraint you get from effective operators, okay, basically you have probably one kind of interaction, and what you're excluding is anything which is above the line, okay. So LHC is excluding that, direct detection is excluding that, okay, and then you may say, well, there is a complementarity for low masses of dark matter, okay, between LHC searches and direct detection searches. Here the logic is different, okay, you have other LHC signatures, okay, here the production of dileptons, okay, and the stronger the coupling to the dark matter, okay, the weaker the constraint from LHC on dilepton production, okay, and so that gives you something which is excluded from below instead of being excluded from above, okay. So there are different messages you can take away from that, okay. One way of thinking is that, you know, if you think that way, okay, you are excluding things from above, okay, and you're being down, okay, the experiment is getting better, okay, better statistics, etc. You go down. With that kind of signature, it's the opposite, you know, they close each other, okay. So basically you end up concluding with the fact that that kind of model is strongly constrained by both direct detection searches and LHC searches. Okay, so that was the first message. Okay, so the second so that was basically a message that, you know, basically is generic for any models in which you have particle ingestion, and that is particle that may be produced resonantly. Okay, if you don't like dileptons, okay, you could build a model where your particle is coupled say to quarks. Okay, and then the constraint is from dijet production. Okay, why not? I mean, that's a bit weaker than dileptons because it's, you know, more difficult to look for digets than dileptons, etc. But the logic is basically the same. Okay, so you're really closing on that kind of model. What is the way out? Well, the way out is to assume that the particle is even heavier, so heavy that it's not yet produced at the LHC. Okay. Another possibility is that, you know, it may be that the first thing you will discover is the messenger and not the dark matter particle. That's another takeaway message, if you want, in that kind of picture. Okay. Okay, so another model. In that part of the talk, I'm going to focus on indirect detection. Okay, for a reason that I'm going to make clear, hopefully. Okay, so there are many different ways of looking directly for dark matter, but one potentially very interesting way is to look for so-called smoking gun signatures. For instance, if dark matter is for some reason emanating into two monoenergetic gamma rays, okay, this is something, I mean, a signature which has no astrophysical counterpart, okay, and which moreover points directly to the mass of the dark matter. I mean, if you observe gamma ray lines like that, okay, given the uncertainty on the measurement, it points directly to the mass of the dark matter. So these two features, okay, make this kind of signature particularly appealing. Okay. So more generally, when we look for so-called spectral features, so what is a spectral feature? So the first instance is, as I said, the annihilation of dark matter into, say, 2 photons, okay, which gives something which is, you know, very peaked around the mass of the dark matter. So on this axis, I'm reporting the energy of the gamma ray divided normalized to the mass of the dark matter. So you have something that peaks around 1. Dark matter is neutral, supposedly neutral, so any annihilation like that is supposed to take place through a loop effect. Okay? So that's one possible signature. Another possibility is so-called virtual internal Bremsstrahlung. Okay, so basically, internal Bremsstrahlung is basically the emission here of a photon or a gamma by some of the charged particles in this diagram. And virtual, okay, refers to the fact that the photon may be emitted by the intermediate virtual particle. Okay, and we will see that this is particularly interesting. In particular because it gives something which has a sort of a peaked spectrum. So for some reason it's okay. So you don't see it, unfortunately, but supposedly there is a continuum contribution here in this figure that is due to the fact that whenever you have dark matter annihilation, you expect to have, say, annihilation into quark-antiquark curves or into gauge bosons, etc., which eventually hadronize or decay into, say, neutral pions, and neutral pions they decay into gammas, and that gives you a continuous spectrum of gamma ray. And this is the typical signatures of dark matter annihilation. Okay, what is less typical is to imagine or assume that you have something like these spectral features. So, so things may be good and bright if you have a situation like that. So you have the continuum here, but you have a strong features. The astrophysical background is perhaps like that, okay, in a given model, and you have really something that peek out from the astrophysical background. Okay, you have this so-called smoking gun for dark matter. That's of course the best scenario. For generic candidates or realistic models, situation is a bit worse. Okay, the background is here, and perhaps you have something like that. And for truly generic candidates, everything is below the astrophysical background. Okay. So one of the issues that you may be confronted with is how to actually have a significant gamma ray feature. Okay, can you get that? Okay, and the motivation is various. I mean, it may be related to the fact that you have experiments looking for this kind of signature, or just because you want to know, what particle candidates can do. Okay, in a specific model, etc. Okay, so it's part of the toolbox of particle theorists. Okay, so this is a summary of the experimental signature, experimental situation. So this here I show as a function of the mass of the dark matter. Okay, the current constraints on annihilation of cross-section of dark matter into gamma ray lines. Okay. Here, to get the eye, I show the benchmark value that you need for the cross-section to reach the relic abundance. Okay, and what is quite remarkable is that both the so-called Fermi-Lat constraints and S limits are quite below this value. Okay, so the current experimental constraints are really good on this kind of signature. Okay, so experiments are really sensitive to that. Of course, you may have heard that there was for a while, a possibility that perhaps there was actually a gamma ray line, something that could not be explained by mundane physics, etc., in the Fermi-Lat data. Of course, the signal is now going away. Okay, but we may still take it as a sort of benchmark. Okay, I don't know if any of you have been working on that when it was popular, but what I want to emphasize is the fact that it's of course so perhaps the signal is fake, going away, etc., but still it's motivating studies, model building. What can you do that actually? I mean, if this is a true signal, can you actually have a model that can produce something like that? And it's not easy. Okay, I mean it's not easy to do it simply, so it's interesting. Okay. So the model I'm going to discuss for the last 25 minutes or so is the following. It's very simple. It's a toy model, okay? And basically, I'm assuming that there are two kinds of new particles, okay? So here, that are coupled to standard model light leptons, okay? So the reason I'm going to couple to leptons is going to be explained later on, but certainly there are less constraints on the couplings to leptons than to quarks. And that's one of the motivation. Okay, so again, it's a toy model. Okay, so the dark matter in that context would be a real singlet scalar, and I have an extra intermediate particle which I take to be a vector-like charged lepton. Okay, By vector lag, I mean something that has no chiral couplings. Okay, both the left and right-handed component have the same properties and couplings. Okay, so one of the things, of course, that I can do once I have a vector lag particle and not a chiral state is that I can put this mass by hand and then just tune it to whatever I want to do. Okay. And then I impose the stability of the dark matter by a Z2 symmetry, and then by the same token, this intermediate particle is also odd under the Z2 symmetry. Okay. So this I call the vector-like particle following this people, but it is also being called fermion portal, or if you win in different contexts. Okay. So it's a very simple model. You know, if you want, it's a sort of it's a bit like this Z prime thing to some extent. I mean, you have the dark matter and an extra particle, okay, which is a messenger between the visible sector and visible sector. Okay. So the basic point I will report on is the fact that for this kind of interaction, okay, the annihilation cross-section is a D wave in chiral limit. I'm going to explain what it means. And then I will show that internal Bremsstrahlung is very strongly enhanced. And to make sense of this enhancement, I will compare to another model, which is, you know, basically a neutral limit. Okay, Majorana dark matter. So I consider annihilation of dark matter into standard model fermions, here taken as leptons. And of course, the important thing to keep in mind is that the annihilation in cross-section, the annihilation in the universe takes place at a relative velocity which is, you know, non-relativistic but still close to the speed of light, while the annihilation in the galaxy takes place at a much smaller velocity. Okay, the relative velocity is of the order of 200 kilometers per second or so. Okay. And then, as usual, you know, what you do is that you look at the effective average annihilation cross-section, and then for a generic model, you may have a different contribution. If there is no velocity dependence, you have the so-called S wave. If it's V square, it's a P wave annihilation, D wave, etc., etc. Okay, and then you may, you know, compute this thermal average, and this is expressed in terms of the Freezer temperature divided by the mass of the dark matter particle. Okay. Typically, in the early universe, freeze-out takes place at this velocity. Again, galactic center much smaller. And of course, as you, I guess many of you are familiar with, I mean, if you have no contribution for no S-wave contribution, then it means that the annihilation cross-section at the galactic center is much smaller than the one that is relevant in the early universe. Okay, so that the cross-section is much smaller. Okay, so this happens in often in many models. The standard case being a Majorana dark matter particle coupled to lagged standard model fermion. So let me recall you how it works. Okay, so the idea is to look at the different possible contributions. The leading a priori contribution being the S-wave annihilation cross-section. Okay, but then since you have a Majorana particle here, okay, and you put them in the S-wave is symmetric. You need they are self-conjugate particles, so you want to have an antisymmetric state. So that means that you have to take this antisymmetric combination, that is the spin zero contribution. Okay, and then you ask yourself, or you can go into a final state which is made of fermions, taking into account the fact that you have chiral couplings, which is the case for the neutralino. Okay, and you realize that the relevant operator is that one. Okay, but to have a matching between these quantum numbers and those of the initial state, you need a chirality flip. Okay, so that tells you right away that the annihilation in the S wave is suppressed by the mass of the fermions in the final state. If this mass is much smaller than the mass of the dark matter, you have suppression. Okay, and this is called chirality depression. Okay, so it's a classic result regarding Majorana particles. You can go then to the next contribution, which is a P wave. P wave, you have now this state, okay? The spatial wave is antisymmetric, so everything is fine, okay? Then in the final state, you go directly to that, okay? Then you have a coupling to this pseudo vector current, okay? And okay, basically, you know, you end up with the fact that the cross-section is P wave, so it depends on the relative momentum of the two particles, okay, and so you get this velocity suppression of the cross-section, okay. So here, again, if an initial cross-section is into light fermions, okay, this is suppressed, and then this is what is relevant in the early universe, but then because it's V square, it's suppressed in the galactic center, okay. So two-body annihilation is suppressed, okay. So now I go to the case of the scalar, the real scalar particle. Again, anything into light fermions, and here I claim that if you do the same reasoning, you get that the cross-section is proportional to the velocity to the fourth power. Okay? There is an extra dependence that appears through this parameter R, which is just the ratio of the mass of the intermediate particle. This is the particle in the T channel over the mass of the dark matter. So of course, the dark matter is supposed to be the lightest odd particle, so this ratio is taken to be larger than that. Okay? So why do you have that? Well, you can do the same reasoning. It's sort of instructive. Okay. Of course, you may have the first contribution is S wave initial state. Okay. So you have two real scalar particles. So this is a CP even state, if you want. Okay. And then you look at the final state. And again, this is spin 0, angular momentum 0. You want to have a spin 0 state. Or if you want, what you need is an effective coupling between the scalar and this effective operator. But for that thing to work, you need a mass insertion. So the effective coupling is chiarly suppressed. Okay, so this is analogous to what you have in the case of the Majorana. The only difference being that you have here a scalar quantity instead of a pseudo-scalar quantity. Okay. You go to the next possible contribution. Okay. The next contribution is okay. So focus on the case of the fermions. Okay. The next contribution would be a coupling to something which is spin 1. Okay. So that is a contribution to this current. Okay. But then it's pretty clear that to have coupling to that current, or if you want to match the quantum numbers, okay, there are different ways of working that out, okay, you need a current here. Now, just out of one scalar, real scalar, you cannot make a current. You need a pseudo-scalar state, okay, or in other words, what you need is a complex scalar, okay. And if you have a complex scalar, or a scalar and a pseudo-scalar, then you may have that kind of coupling. But of course, if you just have this state, okay, this contribution is absent, so you have no P wave initial state. And then the next possibility, okay, so the S wave is chiarly suppressed, P wave is absent, the next possibility is a D wave, okay. So D wave means essentially spin 2, if you want the quantum number, okay. And so the final state, which involves again the fermions, okay, with the same chiral coupling, etc. You may couple to this quantity, which has the same quantum number, okay, the spin 2 quantity. Actually, that thing is nothing but the fermions rational energy tensor and the effective coupling is as follow. Okay, and this is then in the chiral limit. Okay, the dominant effective coupling between your dark matter and the light fermions. Okay. So what are the implications of that? One way of comparing things is to look at the relative cross-section in the scalar case compared to the Majorana case. Okay. Of course, that involves different couplings which may have different normalization, but okay, nevertheless you can plot these two ratios. Okay, and what you get, okay, is that at most this ratio is given by this quantity, and it's suppressed. Okay, so that what is the lesson from that? I mean, the lesson is that if you have a candidate like that instead of a Majorana particle, where it means that if you want to match the relic abundance, okay, to get 3 times the minus 26 centimeter cube per second, where you need a larger coupling for the scalar particle than for a Majorana particle. Okay, so fine. Okay, so far so good. And you do that, okay? So you assume that the relic abundance is fixed by the two-body annihilation cross-section. And then you go to the next step and look at the radiative correction. So the reason I'm looking at the radiative correction is because the two-body cross-section is suppressed in the galactic center, okay, because of the velocity dependence. Okay, so basically, annihilation of the dark matter particle into a pair of fermions is suppressed. Okay, and then you look at radiative correction. Okay, so there are two different kinds of possible radiative correction, and the first case is so-called final state radiation. That is, you have emission from the external legs. Okay. Is here illustrated with an electron and a positron. Okay, but then, as is well known, okay, this kind of effective process, okay, at least in some well-defined limit, okay, is essentially proportional to the two-body process, okay, multiplied by a factor which is sort of universal. Okay. It depends on the nature of the final state, but if the final state is a fermion, it's a universal factor. Okay, but the important thing is that it's proportional to the two-body cross-section. So if the two-body cross-section is suppressed, okay, the whole thing is suppressed, and so final state radiation is effectively suppressed. Okay, but then, since the intermediate particle is charged, okay, you may also have emission by that particle. And then if you look at the propagator here, okay, propagator will be like that, okay, and you take a specific limit, okay, you take this particle to be non-relativistic, okay, and you consider the possibility that the intermediate particle is somewhat degenerate with your standard model particle, or with your dark matter particle. Then the propagator takes that form, okay, this is, you know, close to that, so they cancel more or less each other, and what you get is that as the energy of this fermion of that fermion goes to zero, okay, you have a zero of the inverse propagator. Okay, that implies that if these two particles are almost degenerate, and I will quantify that, okay, you get the initial cross-section peaks for zero energy of the fermion. That means, of course, that all the energy, or half of the energy, goes into the photon, and you get something which has this peaked shape. Okay. The second important thing is that while the two-body process is suppressed, okay, the internal Brahms-Schradlung cross-section is, at least from the virtual state, okay, is unsuppressed, is S-wave. Okay, so you have initial state in the S-wave, final state you have the helicity of the fermions, the spin of the photon, they all combine to give you something which is S-wave, etc. And so you have no suppression. So the bottom line of that is that even though the two-body process, okay, without the gamma is suppressed, okay, the emission of the gamma is not suppressed at non-relativistic relative velocities. Okay, so this is well-known, it has been shown a long time ago, etc. But what I want to show is the specific consequences for the scalar particle. Okay? And so the consequences are the following. The first thing is that you may ask yourself, when I have a Majorana particle, I have a scalar particle, can I make a difference between the two possible candidates in terms of the spectrum? Well, it turns out that the spectrum are exactly the same. That is, normalized to the total cross-section. You get exactly the same spectrum for fixed ratio of the particle in the T-channel and of the dark matter particle. The more degenerate are the particles, okay, the more peak is the spectrum. This is what I showed you when I discussed the properties of the propagator. Okay, but even if the mass is twice larger, you still have sort of a peak. Okay, okay. And importantly, you don't have this continuum contribution because the two-body process is velocity suppressed. Okay, so this is really the spectrum you get from this kind of annihilation process. Okay, so how come that you get exactly the same spectrum? Well, yeah, there are different ways of looking at that, but basically the final state, the only difference between the scalar and Majorana case amounts to replacing, in effective Lagrangian perspective, replacing the field strength of the gamma by its dual, which is just equivalent to replacing electric field by magnetic field, and so it's inconsequential. Okay, but there is a big difference in when you look at the total cross section. So you don't look at the spectrum, you look at the total cross section, and what we found, okay, is that the cross section for internal Bremsstrahlung of the scalar normalized to that of the Merana is larger by a factor of 8. Okay, so if you remember, I showed you that because of the v to the 4 suppression of this process, there was a suppression of the two-body process. Okay, but at the same time you have an enhancement of the Bremsstrahlung. So everything is here. You have a factor of 1/10 roughly, and here a factor of a 10th. Okay. And that means that you get basically a large enhancement of the signal for the scalar dark matter candidate compared to the Merana case. So, of course, it makes little sense to compare the two things, but again, if you fix, what makes sense is to say that the two-body process fixes the relic abundance, so that fixes the couplings, okay, and then you have a prediction for the internal Bremsstrahlung process. And this is what we show in this picture. Okay, so this is again as a function of the ratio of the mass of the intermediate particle to the mass of the dark matter. So here they are nearly degenerate. Here the intermediate particle is substantially heavier. And I normalize the Bremsstrahlung signal to the two-body process at the galactic center. So this is what you need to have the relic abundance. Okay, this is what you have in the Merana case. And you see it's, okay, it's suppressed, okay. And of course, it has to be suppressed because you have extra factors of the fine structural constant, etc. It's a repetitive process, okay. Turns out that for the scalar case, okay, the suppression is much milder, okay. Instead of having a suppression by a factor of something between 10 to minus 2 and 10 to minus 4, depending on the mass of the intermediate particle, you have something which is much smaller.
Michel, I thought that you have to have like close like S and psi in terms of like mass, but here it seems that it doesn't really, like, because even for large splitting, right, between the masses, it's still like, you get a substantial. I mean, it drops, but it's not that bad.
Yeah, there are two things. I mean, there is the shape of the spectrum, which is very peaked if the particles are nearly degenerate. Okay, if you take them apart, then you get a bump instead of a sharp feature. Okay, so here I'm looking at the total cross section. Okay, total cross section is whatever it is.
Right.
So it may be very peaked. I mean, here it's very peaked if you want, and here you have more of a bump. Okay. But in both cases, you have something which is doesn't look like a power law like you have for the continuum part of the spectrum. Okay. But so so I don't know if if you're impressed by that, but basically what we are saying is that look at the ratio is close to 1 here. Okay. I mean it's a radiative correction, but because of this kinematical suppression, okay, the fact because it's D wave, etc., you have this. What at the end of the day is a huge announcement. So let me show you that in a more sensical way. So this is a parameter scan in the case of the Merana particle. Okay, so this is the mass of the dark matter. Here the color coding represents the mass difference between the intermediate particle and the dark matter particle. Okay, so here they are nearly degenerate. Here they are not quite degenerate, but still you have a substantial Bremsstrahlung. Here you have the constraints from S and from Fermilat and from some future experiments. Okay, and all these points are consistent with W map. Okay, so this is basically as good as the model can get in terms of producing a gamma ray spectral feature. Okay, and here you have the constraint from Fermi. And that point roughly is in the region of 130 GeV. Okay, so this is the Fermi 130 GeV excess, if you want. Okay.
So why are there 2 points?
Well, It's because in that paper we were referring at a paper where he found that point and we found that point, and so we just report it. But it's okay. Okay, 1 point. Forget the other point. Okay. That well.
Well, there were 2 lines or something at some point, right?
Say that again.
Weren't there 2 lines that Fermi was reporting at some point too?
Yeah, because you
also
gamma
have
Z.
Yeah, exactly.
You may replace the gamma by a Z, and then you have an extra term from that.
Right.
Yeah. Okay. Yeah.
So this is due to that?
It's really due to a discrepancy between that paper and our paper.
Uh-huh.
I mean, we found something exactly different, etc. But okay, it's really not very important. But the bottom line is that, I mean, that was an attempt, for instance, of explaining this Fermi excess, okay? And you actually see the 2 bumps, okay? Here is from the gamma, it's from the Z, etc. Okay, but you have, okay, so you could fill it, but with some, obviously, you want to bring that from here to there, okay? So you need some boost, okay, which is not provided by the particle model, but has to be implemented by astrophysics or something. Okay. And so for the sake of comparison, this is what we get for the scalar case. Okay? So this is just a reflection of the fact that in the scalar case you have a huge enhancement. Okay? So this is what you get in Majorana, okay, way below the current constraint. This is what you get for the 3 scalar. Okay? Of course there are points which are excluded, but there are many points which are not excluded. But importantly, okay, for instance, you may feedback point. Okay, so again, it's a benchmark. I don't ask you to take it seriously. It's just to show you, the difference between different models. Okay, again, Majorana, and here the scalar. Okay. So, and of course, you can explain without an astrophysical boost, etc., etc. Okay. So. Okay, so believe it or not, okay, that was progress, and so I don't know what to call that. Okay. So just, I'm almost done. So just a few words about gamma ray lines. And by the same token that you have internal Bremsstrahlung, you have a contribution at 1 loop into gamma. You see here it's 2 gamma, but also you have contribution from gamma and Z, etc. Turns out that there was a calculation of this process in the literature, but which was incorrect, so we have corrected it. This is what we got, so I report it because it's new and correct. So this is the cross-section in two photons for some fixed coupling. Here you have the Majorana case, which is very well known. Here is the case of the scalar. Okay, so for those interested, the calculation exists now. Interestingly, you have basically the same strong enhancement. Okay, I mean, look at the scale. Okay, typically, so a typical neutralino particle, Majorana particle at best can give you a gamma ray line at a level which is between 10 to in the range of 10 to the minus to the 4, say. Okay. In the scalar case, you may have a very strong signal. Okay. That's another way of seeing the same result. Actually, all these results has been derived independently by Ibarra and his collaborators. So here is a...
So you can put actually constraints on that, right? Because I mean, since there's an enhanced production of gamma rays, then you can use the data to actually...
Yeah, the model is very constrained.
Okay.
Yeah. But of course, it's easy to relax this constraint. So I basically want to present it in a more positive way, like, how well can a model do compared to another model. Okay. And so... But for instance, if you're an experimentalist looking for gamma ray lines, okay, this is what you get generically for Majorana particle. Okay, I mean, here are your limits. This is our CTA, which is this future Cherenkov telescope array experiment. Okay, well, it's not clear whether it's going to be big, but certainly people are working on that. Okay, so this is how good the field will get in the future. Okay, and here are the prediction for Majorana dark matter particle. Here the prediction for this scalar dark matter particle. Okay, so if you're an experimentalist, this is sort of interesting to see that you have something like that. This is another way of presenting things. There are different constraints on the model. No? So this is the mass of the dark matter. This is again this mass ratio between the dark matter particle and this intermediate particle. Here you have different constraints. Here in blue you have the constraints from Fermi and S. Okay. The reason why you have region where you have constraints and region where you don't have constraints because of these wiggles. Okay. And here the collider constraint. This is LEP constraints. Okay, because of course you have an intermediate charge lepton, okay, new lepton particle, so it's constrained by LEP searches for new charge leptons, regular leptons, and you have a similar constraint from the LHC. Okay, so this is the current constraint from LHC, all current from LEP. The model, to reach the W map abundance, the model need substantial couplings, so at some point the coupling may become too large, and so it becomes strongly interacting and makes little sense in that context. So this is excluded by strong coupling. And this is how things may improve in the future thanks to this CTA telescope. Okay, so as you emphasize, you exclude all the model. So I'm closing here. So possible extension, there are all sort of curious things. Okay, like a very obvious extension is to consider coupling to quarks. Okay, and then it's an easy thing to see that the Bremsstrahlung of gluons, which is a radiative process, okay, normalized to the Bremsstrahlung of photons, given by this ratio. Here is the fine structural constant. Here is the QCD coupling, number of colors, etc. You see that there is a factor. I mean, this ratio is.
So psi now is color, or how does it?
Yeah. This particle is color, of course. And this is neutral and colorless, singlet, etc. So here it's a triplet, and this is a triplet also. But of course, you can complicate the framework. You can make it a SU2 doublet. You can also make this one a SU2 doublet, etc. I mean, potentially you have many possible extensions of that. Okay. The only thing I want to emphasize two little things before concluding is the fact that this ratio is large, okay, and that means that, for instance, when you consider the relic abundance, okay, in that kind of model, okay, the dominant process is actually not annihilation in two pair of quarks, but is this radiative process with the addition of a gluon, okay. So that means that it's different. If you don't know it, then you don't know it, and you may overlook this effect. Okay.
So psi has to be quite heavy, right? I mean,
the what?
Psi. I mean,
yeah. Of course, the constraints from LHC are substantial, like heavy quarks.
Yeah.
Okay, and so the constraints are. But then again, it depends very much of the relative mass. Huh? If they are close in mass, this particle is going to decay into a dark matter particle. This is missing energy. Okay, plus a jet, but if they are close in mass, the jet is soft. And so the constraints, they are not that strong, actually.
So
you could live with 200
and... not close. If they are close.
Close, yeah. So if you want to boost the gamma ray signal, they have to be, you want them to be close, not too far away. Yeah. Like perhaps a factor of 2, etc. Okay. Yeah. But then it becomes a matter of details whether you can actually see or not this kind of jet in the LHC. But the tendency is that they are soft. So the constraints are not, what you would expect naively. Okay, well that's something technical. So I think I'm going to close here. What I'm working on, because it's sort of fun, is the issue of direct detection in this kind of model, which actually drove this same box diagram, but now instead of having photons, you have gluons, etc. And again, I'm interested in how it compares to the Manara case. there are some nice technical issues, like which are related to the fact that, for instance, you may, I mean, you know, this annihilation of dark matter, Mayer dark matter into two photons basically goes through the chiral anomaly. It's a triangular diagram. You start with a box diagram, but really what you're computing is the triangular diagram. Certainly, for one reason, because it's finite, but also because of close relation with the chiral anomaly. And in the scalar case, you would expect that the correspondence, since you couple effectively to the Strategy tensor, is that the annihilation goes through the trace anomaly. But things are a bit more complicated than that. And it's okay, I like that kind of stuff, what can I say? And there are things that I don't understand, so this is why I keep asking, okay? There is something really curious. Okay, there are very few parameters in this model. Basically, the only free parameter is this ratio here. Okay. In terms of that, in this scalar case, okay, the annihilation into two gluons or two photons, etc., for some reason is a zero. That is, you have different amplitude, but they are destructive, and there is a cancellation somewhere. It's something I've never seen. So I keep asking. But you don't have that in the Mayer case. It's monotonic. Okay, and we have worked on different models, etc. It's always monotonic. But for scalars, you have an amplitude zero, which is sort of strange. Anyway, so I hope I've not diluted too much the message here, which at the end of the day was the fact that you sort of models which go a bit beyond effective models, but are very simple. You just have one extra particle. They may come into the S channel or the T channel. These are the two logical possibilities. Okay. And then what you get is specific things like if the dark matter may annihilate into a particle in the S channel. Okay, for sure there is a complementarity not only between direct detection and jet plus missing ET signals, but potentially other signals. Here I've illustrated that with the dilepton production. There is also dijet, etc., etc. Of course, people that do supersymmetry, they know that very well. Somehow things has to be rediscovered in this framework of simplified models. Okay. And then I've discussed, specific signal that you have for this particle in the T channel. So again, something you cannot see using a different operator because you don't see this fine structure. And especially the correspondence between the relic abundance, okay, which fits the coupling, and the strength of your gamma ray signal. Okay. So that was sort of the takeaway message. Okay. Thank you.
So other questions for Michel?
So it's not really related to that matter, but you talk about Z prime models.
Yes.
So Z prime, I mean, it exists, in principle it appears on the neutral current events, right?
Mm-hmm.
So in principle you have also interference terms between, and for example, the neutrino interactions, you could have this.
Yes. Yeah.
So I don't know if these, I mean, if you can put constraints on these that are stronger with respect to what you showed from LHC.
Yeah. Okay. So there are two parts of certainly the LHC constraint has the strongest on this kind of particle. So what you have in mind is more like.
No, because I mean I'm thinking that you have neutral currents, for example, in the sun.
Yeah.
And in the sun, if you have another boson, I mean, okay, we describe pretty well, right? What's happening in so
Yeah.
I don't know exactly.
You mean because this would affect like the matter potential, basically?
Yeah,
Is that what you're aware?
I mean,
Yeah.
it affects exactly how do you.
Yeah, but that's a small.
Yeah. So there are constraints on those, but there are constraints on those. I mean, in units of G Fermi, it's something like 0.2 or something.
Yeah, it's a small constraint.
Yeah.
It's corresponding to one of the mass of the square.
Yeah,
This is the G prime Fermi in some way.
So you say
And so here I'm talking of something which is 10 times heavier at the very least. Okay.
Right.
And assuming that the coupling is the same, so you're down by a factor of 100.
So it's
compare.
really weaker in
Yeah,
respect
yeah.
to what have you
Yeah,
seen.
yeah.
Okay.
Yeah.
Yes.
And then, then there are technical issues, but I don't think that was related to your question. The fact that indeed you may have interference between this resonance and the standard null resonance, but they are far away, and so the resonance effects are small. But but if you find resonance, then these fine effects has to be taken into account. Here it's more like look for breadwinner resonance in the data. Yeah.
Any other questions? All right, if not, let's thank Michel again.